Greetings, my name is Bhavadani Manganathan.
Hi, my name is Ali Afika binti Abdul Aziz.
Hello, I'm Sri Venil anak perempuan Sri Balasubramanian.
Hello, my name is Nur Iza binti Zana Rashidin.
Hi, my name is Nandini Kumara Gudbaran.
Hi, I am Nur Emilia Eliza binti Sabri.
So, for the definition of mean value theorem is one of the important theorems in calculus. This theorem is used in mathematics to solve various problems. This theorem was first proposed by an Indian mathematician, Parameshwara, in the early 14th century. After this, various mathematicians from all around the world worked on this theorem, and the final theorem was proposed by Augustin Louis Cauchy in the year 1823. So, the mean value theorem states that there is at least one point in a given planar arc where the tangent to the arc is parallel to the secant through its endpoints. In the actual analysis, it is one of the most significant outcomes. So, the mean value theorem is used to prove statements about a function on an interval starting from local hypotheses about derivatives at points of the interval. So, moreover, mean value theorem can be easily interpreted using its graphical representation. So, the theorem states that if a function fx is continuous over the closed interval ab and differentiable over the open interval ab, then there exists at least one point z in the interval ab such that f prime z is equals to 0, i.e. the tangent to the curve at point zfz is parallel to the x-axis.
Next, moving on to the application. So, mean value theorem is basically used in parameter space analysis bifurcation. So, bifurcation is represented graphically where the location of the fixed point are analyzed for each possible value of the parameter that exists in the function. So, the main types of bifurcation that exist is saddle node bifurcation, transcritical bifurcation, pitchfork bifurcation, and two of the most popularly known words are subcritical and supercritical. The subcritical refers to the branches that disappears as mu increases, and supercritical represents to the branches that emerges as mu increases. So mu here is the parameter that is analyzed.
Now let's discuss the problem statement. There are two problem statements where the first one is let f be a function defined on the closed interval a and b where f and its derivative f prime are both continuous. So we will show that if f closed interval of AB is a subset of closed interval AB and the modulus of f prime x should be less than 1 for all x in the closed interval AB, then there exists a unique fixed point P in the interval AB. Furthermore, we will prove that P is a periodic point of F and the stable manifold is equal to the interval of AB. And the second problem statement is we are going to prove that if modulus of f prime p is more than 1, then p is a repelling fixed point or we called source, that implying the nearby points are diverged away from p under repeated application of the function. And the second one is if the modulus of f prime is less than 1, then the P is an attracting point or we called sink, that indicating nearby points tend to approach P as the iteration of the function proceeds.
Next is for the problem solution. So in this problem solution, we will continue with Banach contraction mapping principle. So in this Banach contraction mapping principle, we have one important theorem, which is let X be a complete metric space with metric D, and let the mapping of F be a function with the properties that d fx fy less than or equals to alpha dxy for all xy in X for some constant alpha, which is alpha will be less than 1. F is said to be a contraction. then f has exactly one fixed point, p in x, and also the stable manifold of p is equals to x since f and x converges to p as n approaches to infinity for all x in x. So in this theorem, we have two corollary follows the theorem, which is the first corollary states that if the mapping of f is a contraction with fixed point p, then the period f is equals to p. So next is the second corollary, which is let f in C AB, that is f and f prime are both continuous on AB, with the function of AB is a subset of AB, and modulus of fx less than 1 for all x in AB. Then f has exactly one fixed point, which is p, which is denoted by p, which is also in AB. So moreover, the period f is equals to p, and also the stable manifold p is equals to AB. So to prove this second corollary, note that AB equipped with the matrix dxy, which is equals to the modulus of x minus y, is a complete matrix space. So when dxy is a complete matrix space, it satisfies all properties of matrix spaces, such that the first one dxy is greater than 0, and dxy equals to 0 for x equals to y, and dxy equals to dyx, and also the triangle inequality. AB is a complete matrix space when all the Cauchy sequence in AB has a limit in also in AB, which is, in other words, since AB is a complete matrix space, all the Cauchy sequences converges to a point P in AB, and P is clearly a fixed point. Hence, F has a unique point, which is F has a unique fixed point where f prime x is less than alpha for all x in AB. So moreover, by the main value theorem, there exists a point C in AB such that fy minus fx over y minus x is equals to f prime x. Then it implies that fy minus fx equals to f prime c multiplied by y minus x. C is a point between x and y. From the mean value theorem, we can conclude that the modulus of fy minus fx will be equals to the modulus of f prime c multiplied by modulus of y minus x, which is less than or equals to alpha, multiplied by the modulus of y minus x, where alpha is a constant, where alpha is less than 1, and also f prime c is also less than 1. So, we can conclude that f is a contraction on AB. Then, since f has exactly one fixed point, which has been proven earlier, then the fix of f will be equals to p, then the period f will be equals to fixed f, and it will be equals to p. Then period f is equals to p. Then it follows that the fixed f is equals to p implies that f prime p will all converges to p as n goes to infinity, and it implies that every subsequence of f prime x will also converges to p. Then it conclude that the stable manifold of P will be equals to AB. Therefore, we can conclude that F has exactly one fixed point, P, which is P in AB. Period F is equals to P, and the stable manifold of WS, P, is equals to AB.
Next, we need to prove a theorem. So a theorem says that let P is the element of fixed point of F, where F is the mapping from I to I, is such that f is continuous on I and continuously differentiable on an open bounded interval. J is the proper set of I containing P, where the first case is if the modulus of f prime P less than 1, then P is an attracting fixed point or SIC. The second case is if the modulus of f prime P is greater than 1, then P is a repelling fixed point or source. So, in order to prove this theorem, we need to consider both cases. So the first case is highlighted in the orange color, while the second case is highlighted in the blue color. So since fx is moved, f prime p is well defined and is given by f prime p equals to the limit fx minus fp over x minus p from x until p. So the modulus of f prime p is as followed. Suppose that the modulus of f prime p less than 1, then there exists a point where a is the element of real number with a from 0 until 1 such that the modulus of f prime p is less than a less than 1, since f prime x is continuous at x equals to p.
there exists the epsilon greater than 0 such that the modulus of fx minus fp over x minus p is less than a, where the modulus of x minus p is less than epsilon. So, whenever the modulus of x minus p is less than epsilon, we obtain the modulus of fx minus fp is less than a times the modulus of x minus p. Now, the modulus of f squared x minus f squared p is less than a squared times the modulus of x minus p. However, for the second case, we obtain the modulus of f squared x minus f squared p is greater than a squared times modulus of x minus p. Since a is from 0 until 1, then a to the power of n is approaching 0 as n approaches infinity. Again, p is a fixed point of implying f prime p equals to p for all n in all natural numbers. Therefore, we get the modulus of f to the power of nx minus p is approaching 0 as n approaches infinity. Thus, whenever the modulus of x minus p is less than epsilon, then we can conclude that p is a attracting fixed point.
As a conclusion, the mean value theorem, also referred as Lagrange mean value theorem, established an important link between planar arc and its tangent and secant lines. It exerts the extension of a point where the tangent and secant are parallel. This theorem holds immense importance and wide range of application across different fields. It serves as a tool to prove statements about functions by considering local hypotheses concerning derivative, enabling the analysis and comprehension of function properties. In discrete dynamic system, the mean value theorem is employed to examine bifurcation diagrams, helping in determination of stability and appearance and disappearance of branches. Moreover, in integral calculus, this theorem is used to establish specific inequalities and evaluate defined integrals by relating them to the average value of the function over the given interval. Throughout this application, the mean value theorem significantly contributes to mathematical analysis and problem solving in various disciplines. These are the references that we use throughout this project. That's all from us. Thank you.